Oh, this is fantastic that we all teleported here tonight on a Saturday night. I know this is a very special crowd that wants science on Saturday. So I've got some scientainment for you guys. So here we go. You got the backstory from that great intro. I'll emphasize we're talking about the anthropocene, right? That's the climate epoch that we began with the Industrial Revolution. I'll get into that. Let me introduce you to our laboratory for the evening, the Greenland ice sheet, world's largest island, world's smallest continent, I like to think about it. 3 times the area of France, 81% ice covered. It's not flat. It's got this dome of ice on it that has about 7 meters of sea level equivalent in it. And it's a fantastic laboratory to go to utilize because it tells us a story. Ice tells us a story. We go there, we make measurements, and the ice lets go of some of its secrets. That's what this story is about. So I got my experience spending the first 11 years installing and maintaining a network of climate stations on the inland ice, about 20 such stations while I was in Colorado. And I moved here in 2013 to help a team support a Danish funded network of stations. Those are the red circles. They're situated where the surface melting is the most. So collectively, we have like 40 stations now on ice. They're running around the clock, and each of them is sampling what we call the surface energy budget. We're measuring the energy coming from the sun, the energy from the temperature of the air. We're measuring how fast the ice is melting at the surface. And these stations are designed to get closure on the energy budget so that we can really understand melt, not just monitor it, but what's behind melt. And we've learned so much from these stations and others. It's been fantastic as we started out high on the inland ice. Our attention was captured by melt. And then it's like, oh yeah, these outlet glaciers, there's more than 200 of these, at least a kilometer in width, that terminate in the sea. So here's just a summer of 15-minute photos from this camera station. And every time I watch these, you learn something new. So we actually have more than a dozen cameras clicking away around Greenland glaciers. But now let me take you to the single largest outlet of this ice sheet reservoir near the settlement of Ilulissat. It drains this one glacier about more than 10% of the total movement of ice off of the inland ice. That's about 50 gigatons of ice per year. The production of this glacier, the movement, has more than doubled in the last 15 years because of the retreat of the front of this glacier. It loses an area about twice the size of Manhattan Island. It no longer has an ice shelf on it. It was stable for a long period of time, but then it's unzipped, and we later learned it was actually an ocean trigger that caused this retreat. That's what I shot this photo, and you still see the ice shelf intact there. And but it can break away quickly, and this is happening all the time because it's moving forward 30 meters a day, but in an hour or less, it can retreat a kilometer. And that balance of forward motion and back retreat has been, this pattern of retreat. So you can have this mountain of ice detach in just moments. And it's a big place, so I want to give you a feeling for that, the scale of this place. On the left side is the Christianshavn metro station. And for those of you who've walked here to our venue here at the second yellow dot, that's where we are now, teleporting, of course, from planet X31. And here's the far end of this distance is 2 kilometers. Just to give you a feel for the size of that place, it would take 3 of those distances to span that one largest Greenland glacier, or fastest. It's actually the fastest glacier in the world. So you've seen the headlines. You know that Greenland is doing something, and a useful way to talk about that is to follow the meltwater. Kind of like in Washington, D.C., if you want to understand what's going on, you follow the money. A glacier will give its secrets if you follow the water. And so that story begins at the surface, where increasing melting produces lakes like this happening earlier, happening higher on the inland ice. One's about 1.5 kilometers wide. There are hundreds of these lakes, and so it's a melt reservoir that sometimes drains quickly. Here's a photo. It's a little hard to see because the light is so bright up here. I wonder if we could bring that down a little. We got one, second emotion. And what you see here is a lake draining. The next shot is what that hole looks like. Huge fluxes of water. The lakes can drain. And so the point here is that water, which has a temperature several degrees higher than the ice internally, that warm water is, because it's increased, it's more than doubled in this flow of water into the inland ice, that heats the ice internally. Warmer ice is softer, it deforms more easily, and that's one connection that, and I'll go through a list, how factors that the ice is sensitive to climate that are not yet in climate models. The title, Faster Than Forecast. Until we simulate ice that it gets softer under more water flowing in, we won't be predicting how quickly ice goes away. In this cartoon, you see the ice letting this water down to the bed. And the story here, we didn't know this until 2002, that meltwater accelerates the flow by water being incompressible. A kilometer of ice can glide on a thin film of water. So in summer, we see 100% or more speed up of large areas of the inland ice due to this surface meltwater lubrication effect. That's number 2, that is not yet in climate projections of ice going into the future. Under the ice, it's a complex drainage system. We have a lot of water flowing at the bed, and in some areas that emerges at the front. It's still also hard to see because of the light, but this is murky water, dark brown water, because of the connection of the water at the bed and the movement of the ice grinding up sediment, and you have this dark water. What's happening here is the water rushing out, that's that meltwater, forcing a heat exchange between the ocean and the ice. This is flying over some North Greenland outlets where the whole front of this Humboldt Glacier is 110 kilometers of just ice-ocean interaction. And the meltwater that's generated inland flows under again, and you notice how the ice front is retreated there. That's because of the mixing of heat up against the ice, that you can see more clearly just how turbulent this water is. And as the ambient ocean temperatures are increasing, that's forcing a heat exchange between the ice front that's illustrated in this cartoon. As it happens, the warmest waters are below about 300 meters depth, and ocean heat content is increasing globally. That warm water gets entrained and forced up against the glacier front. This undercuts the glacier front, reducing flow resistance right at the grounding line where the ice is grounded against bedrock. So it's just where it's very sensitive to destabilizing the balance of forces that are occurring because the ice wants to move forward and it's being eroded at this point. So very sensitive to ocean warming. This is another factor that's not yet included in the climate projections for the reaction of ice to climate warming. A fourth factor is simply that crevassed areas like this trap more sunlight. That factor is not in the climate models yet. Another factor that models have trouble simulating is a relatively narrow, dark band of bare ice area. And because the model grid boxes tend to be like 100 kilometers, and this region is less than that in some areas. So it's very challenging. It's kind of beyond the scope of models, really. And that's really the message is it's not that people aren't clever that are working on it. It's that encoding the physics of ice motion in climate models, it's not even possible yet because we don't know the physics well enough to articulate it in the type of models that we have, which don't have the resolution that we need to deal with this. All kinds of simplifications produce sluggish ice motion by definition, by design. So we have to rely on observations, and that's telling us a lot. I think that's factor number 5, increasing bare ice area. A sixth factor would be that water flooding crevasses is heavier than the surrounding ice. So if you can keep a crack filled with water, it will drive its way down through ice. The only condition being you need to keep it flooded. And in a warming climate, that condition is being satisfied more often. So that effect we call hydrofracture is what I expect is why this rift on the Petermann Glacier detached during a record warm summer. It was hydrofracture that broke the Petermann Glacier, if you ask me. Proving that is pretty tricky, and we're working on that. We could talk about that offline. Here, we have a new sports car in space. Proud moment for the European Union to have their own new sensor. This is called Sentinel-3. It's seeing the color of ice, the color of snow. It's an ocean color mission. And what's so cool, ice does have color. And we're going to see that. This is a brand new image from this brand new satellite, Sentinel-3. From Greenland, and let me draw your attention to this dark band in the west. Zoom in, and what does this look like up close? This is after a drought, after a period of 2 months without any snowfall, and the surface of this glacier, the bare ice, takes on the color of a parking lot. It's incredible. I was just blown away to see this with my own eyes. I had no idea. So on the ground, we're maintaining our station, and it's really hard to see with the spotlight on the projectors here. There is some color here. I point to an area with color. It's hard to see there. But because this might have been a problem, here's a shot. And can you just make out a kind of a not gray color? It's kind of orange. And let me zoom in like a factor of 1,000. And that's what's there. The darkness you see, it's not dust, it's not soot, it's not black carbon, it's biological. We didn't know this a few years ago. that the surface of the bare ice area, when you get lots of sunshine, produces an algal bloom. And so suddenly, I started as a climatologist. It's like, okay, I'll study ice. It's very interesting. That's glaciology. Oh, we need to become oceanographers as well to understand the ocean interaction. Now what's electric is understanding the biology of this. So glaciology meets biology. We camped for a couple months and made portable spectrometer reflectance measurements. So here's the reflectance spectra. On the left side is the blue colors. On the right side is red. So red is right about here. And this stuff is kind of red in color. You got to look carefully. And it has absorption features. They're kind of dull. But this one is well known for chlorophyll, as is this one, not so well known. And this one, I cannot find literature about that absorption feature, but it's probably carotenoids. And so, okay, back to Sentinel-3, sensing the color. This thing's got 21 spectral bands on it, which are just adequate. Well, by design, they've got one right in this chlorophyll absorption feature, because this is an ocean color mission. And so I take band 9 here and band 11, and the ratio of those two looks like that. So there's a signal from chlorophyll that we can remotely sense from space. And I'm telling you this before we publish it. But it's really exciting. We can sense this stuff remotely. And with the ground measurements, we can confirm what do we see. All right, I'm going to shift from some of those. Those were climate X factors. These were multipliers, not yet in the climate models. This is why ice can go faster than forecast. I want to maybe talk about the what I should have mentioned earlier, perhaps, but why? Why is this happening? You already, unless you're living in a cave or unless you have your head in the sand, you already know that the ice is melting. Let's talk about why that is. Here's a reconstruction since 1840 of the surface runoff from Greenland, and we've got a big increase. It looks like a hockey stick. You've probably heard that term before to describe this abrupt increase. We know that it's producing a lot of meltwater that's coming out of these marine glacier fronts. So why is climate heating? I think since you've teleported with me, to Planet X31, you probably know a lot about this, but let me underscore that the dominant reason why climate is changing today is that humans have become the dominant agent of change. That wasn't true in the past. Climate changes for a lot of different reasons, but today, humans are dominant, about 4/5 of the change. One of the things that's going on is biomass burning. People are clearing land, but we have increased wildfire also because of desertification. That's drying of continent interiors, very much expected with climate change. That's it. It's people and climate change that are burning more biomass. Cement production is not far behind biomass burning in producing greenhouse gases. So we've got, burning of fossil fuels, biomass burning, cement production, and extreme energy. As conventional petroleum dwindles and tar sands become economical, as long as petroleum is at least $40, $50 a barrel, this is economical. OPEC decided to not reduce production, so suddenly this form of extreme energy is not economical right now. Oil companies are doing their best to get this highly profitable, the most profitable substance in the history of money to market, no matter how they can, as long as it's economical. Oil trains or pipelines are key. A key problem, however, is that it's a matter of time till many of these systems fail, despite the best intentions of the engineers. And we have one disaster after the other, like the worst one in the Gulf of Mexico's history, the Deepwater Horizon disaster that went on for months. And somehow that's not enough for us to quit this dangerous substance. It has produced this abrupt change in atmospheric chemistry. Greenhouse gases, these are the ones that just trap a little bit more of the energy coming out of the system or off of the surface. So we're now 42% above on the dominant greenhouse gas, above pre-industrial levels. That's a significant change. Also, when you look at this in the last 800,000 years, you see CO2 here off the chart, also with methane. This is abrupt climate change. This is the Anthropocene. There's no precedent for that. The rhetoric that the climate is always changing is total ignorance in context of these observations. So when you put all that together, it turns out that the human-caused agents of climate change, we have some cooling factors from human activity, and we have some warming factors, chiefly CO2. But you add all these up, and you end up in the warming end, and that's equivalent to 1.6 watts per square meter over the whole planet Earth. Think about one of those little Christmas light bulbs shining at 1.6 watts over every square meter of the planet around the year. That's the net radiative forcing. We're heating the world with 1.6 watts light bulbs over every square meter, every second of the year. So the orbital changes had the climate cooling. We were headed into another ice age. But we prevented that from happening. This is Arctic summer, yeah. So it would have been tough going into an ice age. Thing is, we're going pretty fast in the opposite direction now, arguably too fast. I think we should have stayed right about here. But off we go. This is Arctic summer temperatures. And then that's 2,000 years. What about the next 100 years? It looks like this. We've got our globally harmonious adoption of the Kyoto Protocol scenario here, and we've got our business as usual scenario there. It's clear from the Paris Accord that despite increased ambition to aim for plus 1.5, we actually have to do better than that. Because at these levels, we lose ice sheets. Here's a wonderful reconstruction of climate the last 20,000 years. This is sea level. Sea level goes way up after the ice sheets on North America just disappeared. The ice sheets over Sweden, Finland, they're gone. Scotland, it was covered in ice. Denmark. So that was this sea level rise. Then we had this amazingly stable sea level for like 8,000 years. And that allowed civilization to develop because the tides were predictable. You could build coastal infrastructure. The ocean wasn't coming and going too fast. And that was fundamental to the development of civilization. Without stable sea level, we would not have stable commerce. The scenarios for the future look like this. Let me put this into another way. We had about our Savior's Church of sea level rise, well, more than that, since the last ice age. And what we're looking at, depending on a couple of scenarios, is, in the business as usual scenario, the sea level is right there below Newhound. And the top of those buildings, roughly, we're going to overtop those buildings in a few thousand years. But how quickly we get to the point where the water's spilling over into the cafes, that's the question, right? I've heard that Copenhagen can tolerate 1.4 meters without major disruption, but once you go above that threshold, it's a different story completely. Abrupt sea level rise is already happening. This is from the place where Hurricane Matthew is hitting right now, actually, North Carolina. They've already had an abrupt increase in sea level, so they've got about this much sea level rise since pre-industrial at that place. Sea level rise is non-uniform, depends on a lot of factors, but as the New York Times put it, flooding of coast caused by global warming has already begun. Nuisance flooding, Miami has already installed pumps. I don't know, I think Denmark is doing something. I guess I should know what that is. I think, coastal engineers, planners, they're on it. They're doing the best they can. They're not the, coastal planners and engineers, they're not the people that decide if we melt the ice sheets. This is just a few hours old, this image. So this is seawater inland ruining your lawn. I want to talk somewhat briefly about, okay, how do we tackle this? And the real point is, little tweaks to status quo isn't going to do it. We actually need radical solutions to this problem. That's the only way. Short showers won't get us there. Riding bikes won't get us there. The key challenge, I call this the missing conversation. The conversation, the one you hear, is about reducing emissions, which we need to do. But what about getting from 400 parts per million atmospheric CO2 down below 350? We need to do that, and no one's talking about it. Well, if some people are talking about it. We need to remove CO2. How do we do that? Well, there's this natural technology. We don't need miracle technologies to do this. I was thinking, I actually did the calculation. How much vegetation would we need to plant to sequester 50 parts per million of CO2? And it comes out to about 7 times the area of Australia. But don't despair, because something grows faster than trees and sequesters CO2 about 4 times faster. Does anyone know what that is? He's got it. Weeds grow, sequester 4x faster. I didn't say weed, I said weeds. Weed, now that he said weed. So that'll take you down to like 1.5 Australias or so. That's one idea. This one's meant to underscore resistance, because you probably heard these ones. I had students, I asked them, what are the 3 R's? And they came up with things like this. Revolution. That's kind of what we need. Yes, that's not kind of what we need. We need a fundamental revolution of our energy systems, our economic systems, agricultural systems, you name it. That's what it's going to take, guys, to get to that future that we need to be in. I want to talk about some other radical stuff. Well, it's radical in today's definition of the world, but it's not radical when you consider what we need to do to reestablish a harmonious relationship with nature. And indigenous people, they know how to do that because they've been doing it for a long time. And we need to learn from the wisdom of indigenous peoples who right now are coming out to try to stop a pipeline in North America. Some Sami people are joining the Native American people, and that's happening right now. E. Yes, I think I'll skip that one. Oh yes, E. E for equality. Yes, E's, in this case, we need equal gender across all leaders on planet Earth. There's only 1 out of 10 heads of state are women. We need that to be in unity. It needs to be one-to-one. That needs to be, if you ask me, a law. The E also stands for empower, especially women of color, women in developing worlds who disproportionately don't have access to the other E, education. And so we need to embrace feminism as a fundamental cure or solution, because it's pretty easy to argue that men have fucked things up pretty bad, and that we need to listen to women a bit more here. I'm talking equal pay. I'm talking equal governance across gender, okay? Here's another radical one. It's called forest schools, primary education. So that E is about, the thing is, you cannot deprogram people at the college level. It's too late. They've already gone off to business school. You gotta teach kids to appreciate nature, and that happens when they're this tall, not this tall. And my final slide, we need to be more like Leonardo DiCaprio. So his film that I helped with before the flood it's coming out. So make sure that your conservative friends see the film. Thanks. I guess we have some time. I don't know. Did I blow the time budget? I think we have someone that's helping with the discussion. Now's the time. Or I've got many more slides, but I don't want to overload you.